In this lesson, we're going to be finding inverses of logarithmic and exponential functions. So we're building on what we already know about inverses, and how to create an inverse is to take the y variable, and remember that f of x really means y, and replace it with x, and then take the x variable and replace it with y. So that's how we're going to begin finding the inverse for this function. And this original function that's given to us as an exponential function, we know that because the input variable x appears in the exponent of an exponential expression, and there's a numerical value in the base. And so as we solve for y to find the inverse function, we're going to think about order of operations. If I were plugging in a number for y, I would first subtract 5, raise that to the 7 to that power, and then finally add 1. So the add 1 is the first operation to be undone. Subtract 1 from both sides of the equation. And now we're going to undo the 7 to the power of y minus 5. The way to undo an exponential expression is by putting it in logarithmic form. The base of this logarithm is base 7. So log base 7 of x minus 1 is equal to the exponent y minus 5. Remember that when you write a logarithm, it's equal to the exponent. Finally, one more thing to solve this one for y, and that's to add 5 to both sides of the equation. So 5 plus log base 7 of x minus 1 is equal to y. You can write the plus 5 on either side of the logarithm. The important thing to remember is to put parentheses around the binomial x minus 1 so there's no confusion about what you're taking the log of. Finally, we're going to replace that y with the inverse function notation. That's an important step because we need to state that this function is the inverse function of f, the given function in the example. So f inverse of x is equal to 5 plus log base 7 of x minus 1. All right, let's take a look at another where we're going to be finding the inverse of, this time, a logarithmic function. So let's zoom in on B here. So again, we're going to replace the g of x, which is the y variable, with x, and then bring down the rest of the equation, but replace the x variable with y. Once we've done that, think about the order of operations, things that are happening to y. In order, if we replaced y with a number, we would add 5, take the log base 3 of that number, multiply that by -1, and then finally subtract 2. So the subtract 2 needs to be the first to go. We can undo that by adding 2 to both sides. Now we can undo the times -1 by multiplying both sides by -1. Now we want to undo the logarithm. In order to undo a logarithm, put it in exponential form. So 3 raised to the negative x minus 2, negative x minus 2 is the exponent since the logarithm is equal to it, is equal to y plus 5. Last step, let's subtract off 5. So we have 3 raised to the negative x minus 2 minus 5 is equal to y. Now, to avoid confusion, I'm going to write this differently. You don't have to write this this way, but it will for sure avoid some confusion. So I'm going to write it as g inverse of x is equal to -5 plus 3 to the negative x minus 2. This avoids the confusion as to whether that -5 is actually in the exponent, which it is not, of that exponential function. All right, let's try another. We have another logarithmic function. We're going to replace the y variable with x. Bring down the rest of the equation. except replace the x variable with y. Now we can go about solving this. Since we're solving for y, think about the operations that are happening to y. In order, divide by 2, then take the natural log, times 3, and minus 5. So that minus 5 is the first thing to go. We can undo it by adding 5. Next, the multiply by 3 has to go, and we can undo that by dividing by 3. And now remember that you need to be thinking about the natural log of y minus 2 is the same thing as log base e of y over 2. And so when we're replacing this in, when we're putting this in exponential form, we're going to have the base be the base e, the base to the natural logarithms, which, by the way, is around 2.7. And that's to the x plus 5 over 3, since the logarithm equals the exponent, and that's equal to y over 2. Finally, we're going to multiply both sides by 2. And at the same time I'm doing that, I'm just going to go ahead and replace the y variable with h inverse. Make sure that you're replacing it with h inverse. That's really specifically saying, hey, we just found the inverse function to the original function h that was given in the original example. Also, look at your notation. That -1 appears as a superscript over the h and before the parentheses of x. All right, let's take a look at another exponential function, I believe. Yes, p of x is equal to 3 times 4 to the negative x plus 5. In order to create an inverse, we're going to replace the y with x, and the x with y. Okay, thinking about the order of operations, things that are happening to y. Take the opposite of it, raise 4 to that power, times 3 plus 5. So plus 5 is the first to go. Times 3 is next. Now we need to undo the exponential expression, and that's by writing it in logarithmic form. So we're going to use base 4. And we still have one thing left to do, and that's multiply both sides by -1 in order to solve for y. Of course, y is actually the function p inverse of x. And so there's the inverse function to p of x that was given in the original example. All right, there is one for you to try, so pause the video while you're trying A below. Here is the inverse function, f inverse of x. You may notice that what I did was change the order of the terms, so it's a little bit more obvious that there's a negative coefficient on the 4 to the y minus 3, and then that 5 is a positive number. All right, let's try the inverse to a logarithmic function in B. Pause the video. Here's the inverse function g inverse of x. Also, it would be okay to write this as 10 raised to the x minus 7 over 2 rather than times 1/2. Dividing by 2 and multiplying by half are the same thing. All right, let's take a look at something different. These are inverses, and we're to find show that they are inverses by finding their compositions. So when we say compositions, we are talking about the compositions f of g of x and g of f of x. So let's start with f of g of x. F of g of x is 2 times the log base 3 of g of x minus 6. And now we'll work our way down. 2 times the log base 3 of, and I'm just going to replace g of x with what g of x is equal to, which is 3 to the x over 2 plus 6, and bring down that minus 6. We can simplify what's in the inside of the parentheses, and that's the plus 6 and the minus 6 are going to undo each other, so we just have 3 to the x over 2. Now you may remember this inverse property of logarithms. Log base 3 of 3 to a power is simply the power. So this is equal to 2 times x over 2, which is equal to x. And that is the result that we're supposed to get when we compose two inverse functions. In order to thoroughly show that these are inverses, we need to find the other composition, g of f of x. The same composition, but with f of x this time on the inside. All right, so let's take a look at that composition. So we're going to start with g of f of x. Color code it. So g of f of x equals 3 to the f of x over 2 plus 6. So now let's replace f of x with the expression that's equal to f of x, which is 2 times the log base 3 of x minus 6. And remember that that was, the input was over 2 plus 6. Okay, times 2 and divide by 2 are going to undo each other. So in the exponent now we have log base 3 of x minus 6. And remember that the inverse property, 3 raised to the log base 3 of something, is just the exponent. So x minus 6 plus 6 is just x, and that's the result that we're looking for. All right, it's your turn now to try the two compositions of these two functions. Let's try, and we'll check first, f of g of x. All right, pause the video to do this. Here's what your work should look like for the composition f of g of x. You have to remember that ln just means log base e. So log base e of e to the x minus 2 is just x minus 2. Now let's try the composition g of f of x. So g of f of x. And pause the video to do this one. All right, there's what your work should look like for the composition g of f of x. And it again gives us the result of x, which verifies that these are inverse functions. All right, now let's move on to a discussion of graphing. We can graph a basic exponential fairly easily using a table of values. So I'm going to plug in some x values, a couple negatives and a couple positives. And since y is equal to 2 to the x, when x is negative 2, that's 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. So now let's graph those 5 points. Negative 2, 1/4. Negative 1, 1/2. 0, 1. 1, 2, and 2, 4. What you're going to notice about this is that the graph gets very close to the x-axis but never touches it on the left side, and then the graph rises very quickly on the right side. The domain is the set of all allowable x's. And since x is in the exponent, and you can observe this from the graph as well, the domain is all real numbers, or in interval notation, the interval from negative infinity to infinity. The range, however, all of the y values are numbers that are above 0, not equal to 0. So the y values do not include 0, only those that are greater than 0. Let's take a look at our log function now. The log function may be a little bit harder to create a table for, so let's write it in its equivalent exponential form. The base is 2, the logarithm equals the exponent, so the exponent must be y, and then that's equal to x. So it's going to be easier for us to plug in y values, which are the exponents, and we can plug in those same values that we used before for the exponent, and then compute the x values. If y, the exponent, is -2, then x must be 1/4, and so on, 1/2, 1, 2, 4. So let's graph those points. Over 1/4 down 2, over 1/2 down 1, over 1 down 0, over 2 up 1, over 4 up 2. And this graph should look a lot like, in terms of shape, the exponential function that we just graphed. But this time, it's getting very close to the y-axis. So that means that its domain is 0 to infinity. That is to say that the x values are always greater than 0, or x values are always positive. And the range, or the y values, range from -infinity to positive infinity. So this brings us to an important observation. The domain of a logarithmic function is such that the argument, which is a fancy name for the thing that we are taking the logarithm of, must be a positive number, or translation, must be greater than 0. Right, let's find some domains of different types of functions. The first is an exponential function, no logarithm involved, and you notice that x is in the exponent, and an exponent can be negative, can be positive, can be 0. So an exponent can be anything. What does that mean? The domain for this function, this exponential function, is the interval from -infinity to infinity, or all real numbers. In B, we have a logarithmic function. Now we have to think about the input for the logarithmic function, which is x, and what we said is that x has to be greater than 0, or x has to be positive. We're going to give the domain an interval notation, so x is greater than 0 translates to the interval from 0 to infinity, not inclusive of 0. All right, let's take a look at C. C is another exponential function, and so in C, you see that x plus 5 is in the exponent, so that exponent can be anything that it wants to be, so that means x can be anything that it wants to be. So our domain is again the interval from -infinity to infinity. In D, we have another log function, and so in that log function, we have to concern ourselves with the inside of the logarithm. Whatever you're taking the logarithm of has to be a positive number. So we're taking the logarithm of 3 minus x, so 3 minus x must be greater than 0. That's a linear inequality, so we may solve this one algebraically. Remember to divide by a negative. You're going to switch the direction of the inequality, so x is less than 3. That's the interval from -infinity to positive 3, not inclusive of 3. Now let's take a look at some added layers of complexity. In E, we see another exponential function, so that means we don't have to worry about the logarithm, but we also see a square root. Now, what do you need to concern yourself with in a square root? That is the inside of the square root, 9 minus x squared, can't be negative. You can't take the square root of a negative, but you can take the square root of positive numbers, and you can also take the square root of 0, so that means that 9 minus x squared is greater than or equal to 0. This is different from logarithms. This is a nonlinear inequality, so we do not want to solve this one algebraically. I'm just going to factor here 3 plus x times 3 minus x is greater than or equal to 0. Use a number line. Mark off the two values that make the polynomial 0 on the number line. And then let's use a test value. Something to the right is usually easiest, so let's use 4. 3 plus 4 is positive, 3 minus 4 is negative. Multiplying those two together, I get negative. Both of these factors are multiplicity 1, so they both have sign changes in them. And we are looking for the place on the number line where the polynomial is equal to 0 or greater than 0, which is positive. So we're going to pick that interval inclusive of those two endpoints, the interval from -3 to 3. In f, we have a logarithmic function, so we need to concern ourselves with the inside of that logarithm. The inside of the logarithm, 5x minus x squared, has to be positive, not equal to 0 this time, because you cannot take the log of 0 like you can take the square root of 0. Again, this is a nonlinear inequality, so factor, but don't try to solve this algebraically. So we can mark off x equals 0 and x equals 5 as places where the polynomial is equal to 0. Let's plug in a larger number like 6 that would be in the region to the right. 6 times 5 minus 6 is a negative number. Multiplicity 1 again, so there's our pattern for the signs. This time we are looking just for the values that make this polynomial greater than 0, not equal to 0. So that would be the interval between 0 and 5, not inclusive of the endpoints. Let's take a look at a couple more. Another exponential function in G. This one doesn't have a logarithm, it doesn't have a square root, but it does have a division. And with divisions, we know that the denominator can never equal 0. So that means that x can never equal 0. On a number line, that would look like just the number 0 excluded. So that's going to be the interval from -infinity to 0 union interval from 0 to infinity. And lastly, we have a function p of x that's a logarithmic function. So we need to concern ourselves with the inside of the logarithm. And the inside of a logarithm has to be greater than 0. And we've never solved one that was a rational expression before, but the rules of division are just the same as the rules for multiplication with one exception, and that exception is the zeros. So our two factors are x and x minus 3. 0 and 3 will cause those factors to be 0. If x equals 0, our fraction is equal to 0. If x equals 3, our fraction is undefined. Now let's use a number on the right side of the number line, maybe 4. 4 over 4 minus 3 is a positive number. Both factors are multiplicity 1, so plus minus plus is our pattern since the there is a change in sign at each one of those critical values on the number line. And now we are looking for just where this expression, this fraction, is greater than 0. So that's going to be on the left and the right of the number line. So that's the interval from -infinity to 0, union interval from 3 to infinity. The fact that at x equals 3, the expression was undefined, didn't matter for this inequality. However, if we had a square root inequality where we're setting it greater than or equal to 0, that would mean that 0 would be included and 3 would not. Well, that's it for the lesson.